question.
Do you have a physical pointer? Okay, this works.
No, this doesn't work. No, you can't use this. Because only I can see. It's reflective. No, you can see.
You have a low-tech pointer.
But
So actually, you're probably blind.
you have to make correct angles, then you see.
Okay.
The lowest tech pointer in existence is the finger. So
Or this. Somebody's.
The well is dangerous for the screen.
That's dangerous.
Then you should be careful, don't ask the wrong question.
all right.
That's why I did for plastic knife.
Yeah.
They will let you on the airplane. Okay, so I'm going to continue to talk about the project that Andy was just telling us about. And as he said, this is work in progress with Natalie Gaiazzo and Andrew Knightsky. And you'll rapidly see that I really don't understand what I'm talking about. But I thought I'd talk about it anyway because with such a great expert audience, I'm actually looking forward to some of the feedback that we might get out of some of these points I'll talk about. So a paper is in progress, and it should appear, as you've already noticed, sometime within the next 10 years. Okay, so we saw in Andy's talk that the circle compactifications of four-dimensional n equals 2 theories produces this interesting class of functions, misnamed Darboux coordinates, which satisfy a TBA-like equation on the board anymore, and which can be used to construct high-scale manifolds.
Why are this name?
Because they're infinite, it's an infinite class of functions. They're not, I mean, if you take a basis of the lattice gamma, then that will be a set of coordinates. And which basis you should take will depend on different coordinate patches and so on. But it's an infinite collection of functions. So I don't like this name, but this is the best we can come up with. Anyway, I'm going to call them Darboux coordinates. And moreover, for the A1 theories, these functions can be constructed very explicitly in terms of Bach-Goncharov coordinates on the moduli space of flat associative connections. So the motivation for the work I'm going to talk about was that we wanted to find another physical interpretation of Y gamma. And the answer turns out to be that we should think of these as vacuum expectation values of infrared line operators. And so we're going to be aiming for a formula like this one here, where we'll define some kind of line operator in the ultraviolet. It will have an expectation value once we make the corresponding loop operator on R3 times S1. And it will be a function on this moduli space M that Andy's been talking about. And the function will look like this. It will be a sum over the electromagnetic charge lattice of these Y gammas with some integer coefficients, which will turn out to be indices of a new kind of BPS space.
So you're reckoning these operators on the S1?
Yes. This formula corresponds to R3 times S1.
Excuse me, what is VEV and
VEV. VEV. It's short for vacuum expectation value. It's physics jargon. The vacuum in question is a point in this moduli space curve.
You know what IR and U?
Well, now is not the time to start explaining. But the discussion session would be okay. Okay, so anyway, while trying to unravel this kind of formula, which we'll get to later in the talk, we found some other things which I think are of independent interest. This VEV can be viewed as a kind of classical limit of an expression f of L that we assign to a line operator L, where we sum again over the electromagnetic charge lattice, but instead of the Darboux coordinates, we have some formal variables x gamma which obey a Heisenberg relation like this. And the interesting part here is that the coefficients are the characters of a representation of SU2. That is to say, they are a positive finite sum of Q integers with positive integer coefficients. And in this talk, Q is Y, because of where it came from the...
So that y is not the same as the y again.
most definitely not. Geez, I never thought about that. So let's see. So a Q integer is y to the n minus y to the minus n in the form minus y. Inverse is the character of an irreducible representation of SU2 dimension n. Okay.
Sorry, what's your x here?
And I think it's n.
You said it was
Use
a
L'Hopital rule. Yeah.
You said that it was a classical some kind of operator.
It's classical limited in quotes. I wish I could make it more precise. I'll say more about it later.
Excuse me, what's your x gamma there? Are they the same as y?
X gamma. X gamma are formal variables, which all we know about them so far is that they satisfy Heisenberg relation.
Oh, okay.
They can be thought of sort of as some sort of operator versions of.
Right now, they're just bookkeeping devices. Okay, they're just bookkeeping devices, and they're not going to get very much further than that. But in fact, I think a lot of the topics at this workshop suggest that there's a deeper meaning to these X
So you
gamma.
want to think of FL as L with a head like an operator of some sort.
Well, we'll see. We'll see. This is just a bookkeeping device, a generating function for these objects, which I haven't told you about, and which I will tell you about. I'm just trying to give you a taste of the kind of results we're talking about. You're not expected to understand all the terms, because I have to explain them in this outline. Okay, so what we found once we introduced this f of L was thinking about it gave a nice physical proof of this so-called motivic constitutive wall-crossing formula. And moreover, in these A1 theories, there are concrete algorithms for computing these quantities. And finally, these f of L's seem to be related in ways I'd like to understand better to the quantum geodesic operators in quantum microwave theory, which is how I'm justifying my presence here.
Related, do you mean equal?
Well, let's discuss equal. They satisfy the same operator algebra. That's all I'm saying. Okay, so here's the outline. So I'm going to talk about some generalities about supersymmetric line operators. And then I'm going to introduce these new BPS states, which seem to be very useful. We call them framed BPS states. And then I'm going to talk about a physical picture of how we think about the wall crossing phenomenon for these framed BPS states, called the halo phenomenon. And it will be a rather qualitative physical picture, but it will lead us to some definite mathematical formulas. And so indeed, I'll talk about the wall crossing formulas. And then I'll introduce a deformed non-commutative product of line operators. And then I'll introduce a mathematical notion called formal line operators, which I think is totally independently of all the physics. I think it's of intense mathematical interest. And then I'll get to this formula I was just showing before, where I expand the VEV in terms of the Darboux coordinates. That's the Darboux coordinate expansion. Time permits, I'll tell you a little bit about how we can calculate some things, really calculate things in the A1 theories, and I'll summarize and mention some of the problems.
Is Howell's have anything to do with attractors or not?
Yes. Well, yes, absolutely. It's a modification of the old supergravity story. So, okay, so let's talk a little bit about supersymmetric line operators in a four-dimensional n equals 2 theory. So I'm going to think about this four-dimensional n equals 2 theory as a perturbation from some renormalization group fixed point called S. And the only thing we need to know about it is that it has SU22/2 superformal symmetry. And a line operator is it's to be thought of as a boundary condition on ADS2 times S2. So Kapuskin's idea was that you look at the operator as a line defect in 4 dimensions. You look at the infinitesimal neighborhood of that. It's conformal. The infinitesimal neighborhood is conformal to ADS2 times S2. If you're very close to that defect, all you need to know is the properties of the ultraviolet theory, and you put a boundary condition on that. So it's not really an operator. It's something you can insert in the path integral. And the important thing for us is that in the presence of a line operator L, the Hilbert space of the theory before is modified to a new Hilbert space, H sub L. And in the hierarchy of locality that people are exploring with these higher categories and so on, L should probably be thought of as an object in a monoidal category. The subcategory that we're going to be thinking of, or the line operators that we're going to think about, are somewhat simple. They just stretch along the time direction. So you think of them as a point in space. That's a good way to think of it. Just a point defect in space. And we're going to restrict to a class of line operators which, moreover, preserve 4 supersymmetries. And so let me say what I mean by preserving 4 supersymmetries in a little more detail. So we're going to introduce a phase, zeta. It's going to be the same as Andy's zeta. And we're going to define a superalgebra, which is isomorphic to OSP4 star / 2, but the embedding in the superconformal algebra will depend on zeta. So let me define it. So in the superconformal algebra, there's a parity involution. X goes to minus x around this point, x equals 0, where the line operator sits. And there's also a U1R symmetry. So we combine a parity involution with the U1R rotation by this phase zeta. That turns out to be an involution, and you take the fixed subalgebra of that involution. And the even part of the subalgebra consists is a sum of 3 Lie algebras. One is the conformal algebras along the quote world sheet of the line operator. The other is the rotation algebra for rotations in space around x equals 0. And then the other is the SU2R symmetry. That doesn't depend on zeta. But the on part of the superalgebra does depend on zeta. And here I just write down the Poincare supercharges. So in n equals 2, you have supercharges Q, QR. And the ones that are fixed, you see the parity operation basically multiplies by a gamma matrix. The R symmetry rotation rotates by zeta, and so a fixed point of that involution looks like this, and so those are the preserved supersymmetries.
So, as zeta specified the embedding was as an abstract algebra, it's independent.
That is correct. That is correct. So they're all as an abstract superalgebra OSP4 / 2, but zeta, as you said perfectly, specifies the embedding. So there's a circle's worth of non-equivalent embedding. And so I'm going to say a line operator that preserves this subalgebra is a line operator type zeta, denoted L sub zeta, and then it will have some other labels. Now later on, I'm going to be analytically continuing from zeta, which is a phase, to zeta, which is in C star, and then it should be directly thought of as the zeta in Andy's talk. Okay, so what are some examples? Well, there are the Wilson operators, Wilson line operators. So if we take a compact simple Lie group, then we can associate to that an n equals 2 theory. Just take the vector multiplets in G. And then if we choose a representation, then we can take a line operator like this. It's path-ordered exponential along the time direction at the spatial point 0 in the representation R. This phi here is a scalar field in the vector multiplet, and the A here is the gauge field. There's a magnetic dual of this, where we take a co-character that's a homomorphism from U1 into A maximal torus of G, and we use that to embed a monopole solution, and that defines the 't Hooft operators. And then we can combine these into Wilson and 't Hooft operators, and these are labeled by certain collections, curly L, which sit between, let's see, this is the co-root times the root lattice and the co-character times the character or weight lattice. And they sit somewhere in between and should be modded out by file transformation. So those are just examples of these line operators. Now these line operators can be added. It's an additive monoidal category. So so the Hilbert space for the sum of line operators is the sum of the Hilbert spaces, and L is simple if it's not the sum of other line operators. And they can be multiplied. You can insert two of these things in the path integral. And now these are line defects, so so you should expect that if you bring these line operators close to each other, then there should be a locality says there should be an operator product expansion, and you should be able to replace those two defects which are close to each other by a sum of line defects. And this is a commutative multiplication because there's no natural ordering which points on R3. And this has been the study of some pretty deep papers by Kapustin and Solina. Okay, that's our monoidal structure. Now I won't need this for the rest of the talk, but let me just say it quickly. So you can also define the notion of mutual locality of these line operators. You see, if you have two line operators, they break the rotation symmetry, clearly, down to rotations around the axis that connects these 2 points. Okay, and now you just require that the Hilbert space in the presence of these two is a representation of the group U1 of those rotations, not just its universal cover. And for example, if we are thinking about explicit Wilson and Hooft operators, that limits which ones you can have to a kind of condition like this, a kind of Dirac quantization condition. All right, so that's all we're going to say about generalities on line operators. Now, let's talk about framed BPS states and this thing called protected spin character. So, as Andy has nicely described to you in great detail, in an n equals 2, d equals 4 theory, we have a local system of electromagnetic charges over the vector multiplet moduli space P. And if L is a simple line operator, then this Hilbert space in the presence of this line operator is graded by the charge lattice. And so we write the graded components HL gamma. Truth be told, there can be a little shift there. You can sum over a torsor for gamma, not just gamma. And that sounds fancy, but I'm saying something very, very simple. Think about pure SU2 gauge theory. And the states in that gauge theory are all going to have even electric charge and some normalization where a quark would have electric charge 1. Well, okay, so then the charge lattice, gamma, would have even electric charges, but of course I can still put a Wilson line in the fundamental representation. You can't stop me from doing that. And then all the charges would be odd, and the odd integers or torsor would be even. So that's all. Okay, now we have these preserved. Now let's take an operator type zeta, and let's restrict the supersymmetry algebra to one of these components. And so this is what the supersymmetry algebra of the preserved supersymmetries looks like. And the interesting thing here is it's E plus the real part of Z gamma over zeta, where Z gamma is the thing that Andy talked about. Okay, so now combine that with some hermiticity conditions, and you find a new BPS step. So, in Andy's talk, we had the old-fashioned, I'll call it the vanilla BPS down, where the energies had to be above absolute values of gamma, and the vanilla BPS states were states in the absence of line operators that saturated them. Well, we think the spectrum in the presence of the line operators, this is why the Hilbert space in the presence of the line operator is different. We think the spectrum of the energy looks like this. It has a new BPS bound, which is lower, and then there's generically a gap to some states, and then there'll be some continuum above these kinds of discrete states. And I'll say what I think these states are at the moment. Now, the states which saturate this bound we call framed BPS states. And if we look at this space of framed BPS states, as far as we know, these are all finite dimensional vector spaces. Remember, the line operator is just a point in R3, so there's a rotational symmetry around that point, and there's an unbroken SU2R symmetry. And so we can now take the following trace. This defines what we call the protected, or the framed protected spin character. It's a trace over this space of BPS states, y to the 2j3 minus y to the 2i3. And the nice thing about this is that this guy vanishes on massive representations. And once you realize that we've missed something for years. There's also a protected spin character for vanilla BPS states.
What's J3 and I3?
So J3 and I3 are generators of the spatial rotations. And you choose your favorite generator of a spatial rotation and an SU2R symmetry. And so for all the vanilla BPS states, if you factor out they have hypermultiplet, then you get a space of BPS states H prime, and you can define it. Now this protected spin character, which was suggested to us by one, you see we were sort of complaining about how we were working with spin characters, but we knew in our heart of hearts that spin characters are not indices. Spin characters, there's nothing protecting a spin character. It can jump. And yet we were getting good results with it. And not only that, in work I did Iaconescu and in lots of papers of Demofsky and Gutkov and examples we were looking at, we were using these spin characters, and yet we were matching to the mathematical results, but we had no a priori reason to think that the spin character was an index. So one suggestion was quite excellent, because you see now you can put in a coupling to the R symmetry, and you actually can prove that that's an index. But then why is it the spin character? Well, it seems to be the spin character in all the examples we've looked at, and so we are formulating a conjecture based on these examples, the strong positivity conjecture, which is that in a four-dimensional n equals 2 field theory, the protected spin character is the spin character. So in other words, the R symmetry of the BPS states is such that this extra modification, which justifies its being an index, to actually change the answer from the spin character. Now, this is actually not true in supergravity. In supergravity, there exist examples where the spin character jumps, and it jumps not across a wall of marginal stability. Okay? So there's something very non-trivial here. In fact, if you interpret these framed BPS states as you can in terms of some Dirac operator zero modes on manifold moduli spaces, it's saying something non-trivial about that. Okay. So we've got this index, this y-dependent index, and like the BPS indices that Andy talked about, it can jump as a function of parameters. So now let's ask, how does the spin character depend on the vacua of the four-dimensional theory and on this zeta, which determines our lineup group? Well, it's an index, so it's piecewise constant, but it can jump when in the spectrum of energies here, this gap goes to zero. Now I'm going to try to explain why we think this spectrum looks this way. So I have to ask the mathematicians to bear with me here, so I'm going to do some heuristic physics. So we think that the general framed BPS state looks in the infrared just like some infinitely heavy BPS dion charged gamma. You know you can introduce Wilson lines into the path integral by putting some infinitely heavy quark, right? So this is just that idea. And this is some point-like defect. But now let's imagine that we split the charge gamma as, I'll call it gamma core and gamma halo. Okay, so we have a point-like defect with charge gamma core satisfying its BPS down. And now imagine we have a comet. This gamma halo is like a cometary particle. So it has a rest mass. It's a BPS particle. So it has a rest mass absolute value of C gamma H, and then it has kinetic energy. Okay. So that's above the BPS value. But now what you can do is you can show that in addition to comets, there are planets. There are bound states of gamma H particles in the presence of this infinitely heavy dion of charge gamma C. And you can really prove that, because you can take the configuration of electromagnetic fields and scalar fields produced by this core, put a gamma H particle in as a probe using this action, standard action, work out the energy and see where it's minimized. And it sits in a sphere of radius, which we call the halo radius, which is given by this formula. So this is the inner product that Andy talked about. This is the same central charge Andy talked about. And this is the formula for the halo radius. So to answer Samson's question, this is a close analog of Frederick Deneff's formula for the bound state's radius of two supergravity dions. Now, you can also calculate the energy of this bound state, and it's this plus that, which is, because Z is linear in gamma, just the frame BPS bound. So these are framed BPS states. Okay, so now you see that's what the continuum or the comets. The bound state is the planetary orbit, and the gap, you see, now is the absolute value of Z gamma H plus the real part of gamma H over zeta, and the gap closes across BPS walls, which are associated to a charge gamma H, and is a real codimension wall in B times C star, where Z gamma H over zeta is a negative real number. So Andy was talking about BPS rays. The relation to his BPS rays is if you fix U, then in the zeta plane, this becomes one of those rays. Okay, so now there's the standard mechanism for losing these BPS bound states. As we cross this wall, the formula for the halo radius goes to infinity, and it exits the Hilbert space. Now, in fact, you lose more than just one kind of bound state here, because there are loads and loads of bound states that you lose when you cross this wall. You see, if I take particles, BPS particles, whose charge is parallel to gamma H, they're all mutually BPS. So I can just add these in, and they all sit in this halo radius, but they don't interact. And so we can actually build up the Fock space. Now, I'll say what that Fock space is a little more precisely in a second. And, but the point is that we lose entire Fock spaces, or gain entire Fock spaces, depending on which direction we go, as we vary zeta or other parameters and cross this wall. So the stability condition, this is the analog of the Deneff stability condition. The stability condition is this condition here. All right. So, let me say what the Fock space is a little more precisely. So we had this space of these BPS states, and that's almost going to be our space of creation operators, but not quite. We have to tensor that with a finite dimensional representation, an irreducible representation of SO3, of dimension, the absolute value of gamma core inner product gamma C. And the reason for that is that, you see, when you have a dion and a halo particle, they create spin in the electromagnetic field, and so there are also those spin degrees of freedom. Another point of view you might like is if you can think of these particles sitting on the sphere as being like electrons in a uniform magnetic field. And the strength of that magnetic field is gamma C inner product gamma H, and then you have the usual Landau level degeneracy. So however you like to look at it, we have a finite dimensional vector space V here, which is a space of creation operators, and then we simply apply the Fock space construction to those creation operators, and that's our halo Fock space. And now actually this is a Z2 graded space of creation operators, so there are fermionic and bosonic creation operators, and the hypermultiplets of the 4D theory are fermionic, the vector multiplets are bosonic. In general, if I write the protected spin character of these vanilla BPS states, stand it out in a Y, then the AMs here for M even are positive. They correspond to fermionic accretion operators. M odd correspond to bosonic operators, and for M odd, these A sub M's are negative. Okay. Now, this was for one kind of particle of charge gamma H. If you have a BPS particle with charge parallel to gamma H, the same story holds. And so in general, this is what our Fock spaces look like.
So this chi directed depending on the beginning, it's not the A, right? It's kind of function. Chi, which had this exchange relation.
X, yes.
X.
X does not appear yet.
It's not that, it not extend that Fock space.
It's going to be related to the Fock spaces, as you'll see in just a few slides. But it has not yet appeared.
Concern is when you leave this should we find that within this allocation function?
Your,
Yeah.
I'm not sure. I mean, you have something that couples to the stem of the part. That's the key thing. Yeah, you do, of course. Yes, of course you have the rotations coupling the spin. Yeah. Yeah, so I would think that, yeah, okay. I don't know your partition function well enough to say for sure, but I would think that you can extract BPS degeneracies, right?
That's the question.
I guess that's what Samson was asking earlier. Can you know, is everything encoded in the prepotential?
No, for the Z, whatever.
Well, the Z, you get Z from the prepotential. Yeah, it's a good question.
The way,
Can you extract first? I guess my counter question would first be: can you extract even the BPS degeneracies from your partition function? I don't know the answer to that, so I certainly don't know the answer to this. Okay. Any other questions? Okay. So that's the those are the physical pictures. Now I'm going to write some mathematical formulas to describe this wall crossing. So the most naive thing you want to do. Okay. So what are we trying to talk about? We're trying to talk about how these framed protected spin characters change as we vary U and zeta. Now the most naive thing to do here is to write a generating function by introducing little x gamma, which generate the group algebra of the lattice. And let's call that the classical generating function. And then the gain and loss of the halos, that physical picture I was showing you, where the halos come and go, well, you just take this halo Fock space and you take its partition function, and this is the way, and this is what it looks like. Just a standard Fock space formula for particles, where the m's run over some indices and these integers a enter. So remember I told you that for the fermions a was positive, for the bosons a is negative. It works just the way you expect. So that's all this is. But this formula is a little awkward because it's awkward to try and split gamma into a core charge and a halo charge. And in fact, as you move around in the moduli space, that distinction is not even really invariant. And it turns out that there's a much cleaner way to express this gain and loss of Fock spaces. And that is to introduce these quantum X gammas now, which are just bookkeeping devices at the moment. Okay? So they just satisfy the Heisenberg relation. We'll just define this. I've defined protected spin characters, so we define f of L to be this expression. Okay, so now I want to talk about, express the wall crossing in terms of this f of L. Now, these walls, W hat of gamma H, maybe I'll write the formula for that. So, W hat of gamma H is the set of U and zeta such that Z gamma H of U over zeta is a negative number. And we're only interested in those walls for which omega is not 0. So they divide up B times C star into chambers. And so these indices are different in the different chambers. How do they change? Well, here's the wall crossing formula. So you go from negative this chamber where the imaginary part over zeta is negative to where it's positive, across some wall W hat gamma H, and then the formula is that F in C plus is F in C minus conjugated by an operator, which only depends on X gamma H, and is a product of these quantum dilogarithms. So for me, the quantum dilogarithm is this infinite product here. And then the A sub m's enter here. They tell us what powers of the quantum dilogarithm take. Okay, so let me make a few comments about this formula. So the first thing is that this just expresses how we gain and lose Fock spaces. Now the second thing is, in our project, our motivation was actually, this third part of our project, our motivation was not to prove the KS wall crossing formula. We couldn't already do that. But actually it came out as a corollary, nice corollary of this discussion, that you can get a proof of the so-called motivic KS wall crossing formula. And the idea is similar to what Andy was saying. So you have these chambers, and here's chamber 1, and here's chamber 2, so just fix 2 chambers. And then there are bunches of walls with different chambers, and you can consider 2 different paths that cross these walls in 2 different ways. And each time you cross these walls, you get conjugated by these quantum dilogarithms. And on the other hand, F of L in this chamber is related to F of L in this chamber by some definite transformation. There's some definite transformation from here to here. On the other hand, it's expressed in different ways as multiplying up these different quantum dilogarithms, but there has to be path independence. They have to give you the same net transformation. That is the KS wall crossing formula. That path independence. Now, this discussion I've given here is consistent with a nice paper of Donofsky, Gukov, and Seukelman, although they had a different physical picture from what we've got. But everything I'm saying, I think, is consistent with what they're saying. And now let me come to this classical limit. So if you if you just put y equals 1, then this formula here, y equals minus 1, then this formula here on the commutative variables becomes diffeomorphism. And so if we're interested in the VPS the framed VPS indices, not the protected spin characters, but just the framed VPS indices, then the wall crossing formula becomes much simpler. We just introduce, actually, because it's y equals minus 1, a twisted group algebra, but they're still commutative. And we have a diffeomorphism of these commutative variables, which is given by this cluster transformation. So that's all I mean by the classical way. Okay. Now, the last thing I want to say about this sort of general stuff is that
You said that decomposition between gamma C and gamma H is not consistent everywhere, but
I said it's not canonical.
Yeah,
I
canonical.
didn't say there's nothing inconsistent.
Yeah.
It's not canonical. The decomposition, and you're going to see an example of that in just a second. But ask your question.
No, but you said that this the quantum.
You see, this gets around that. I never had to tell you how to decompose. You see, if I were trying to do it classically, I would have to tell you. We can do it. It's a little bit. You can express this by summing gamma C over all the relevant gamma H's and taking the quotient of the lattice by the sublattice generated by gamma H, blah, blah, blah. There's a procedure to deal with it. It's just awkward. Okay. So at the moment, this quantization is just, it's more, introducing these Heisenberg variables just makes the mathematics much more elegant. Okay. Now, of course, there's something deeper going on. That's all I'm saying.
But the thing there is no, this x of gamma is not something nice in H or some operator that you can construct. It's just really bookkeeping.
Unfortunately for me, in this talk, it's really bookkeeping. Do I believe that there's a deeper interpretation of X gamma? Of course I do. But I cannot construct X gamma for you out of the fields, the fundamental fields of the any
It would be
conjugation.
cycle, but surface and this kind of formulas are more natural.
Sorry.
If it would be, if gamma would be some surface and not the line,
Well, gamma is a charge. Sorry. Gamma
but
is a,
associated to some lattice.
oh, you mean when we're talking about surface operators?
Right, then it's more natural such formula, right? Well,
I'm not sure what
surface is
you're talking
intersect,
about.
then there is intersection.
So that these are lines. So
Okay. You want to put line operators and surface operators? Yeah. Okay. Well, maybe that's the right a route to go. But
Every
But I think it's like the boundary observer. It actually X gamma is unobservable.
Okay, so
Oh,
then
sorry.
I repeat now that is X some kind of observable, good or chiral whatever, some observable which is possible to construct
Well,
in
there
the
is-
image.
So there is a related story where you introduce a negative count, and if you write this to the Sealer model on the same space M, then the point where the line operator
Yeah.
becomes a boundary,
Yeah.
condition.
and then X is an operator of that.
And that's XW is the open string which connects, which leaves off this grain, and you form local algebra which
Okay, that sounds quite right.
Also in the quantization story, this is counts in the operators.
Indeed. So then, yeah. So I understand that you can quantize these Fock coordinates in quantum space. Yeah, I understand that. But and I think indeed, I think that there will be some, interpretation of these X gammas along those lines. I'm certainly not saying no. I'm just saying I don't know how to write all the details for the general analytic theory. I think both of what you said is correct, but I haven't worked out all the
See,
details.
that's this quantization is not something which should be artificially that's not like comparisons, but that's something which comes out of the
Right, yeah, sure. In your story with that, yeah, absolutely. No, sure. In your papers and your Teschner's paper, these X gammas are actual operators on a Hilbert system. Absolutely. Yeah, I'm not saying that's not true.
it's just not clear that there is a Hilbert space here.
Exactly.
Yeah.
Exactly. That's why I'm avoiding saying yes, it's the same, because
I was not asking about Hilbert space as an operator in the gauge zone.
Well,
Without
operators
Hilbert.
usually atoms.
It's usually it's good, but sometimes in deformation passage, whatever, there is no Hilbert
They're
space.
the operators.
But they're operators.
No.
Okay, there's a ring of operators. That's all we're saying.
Yeah,
We're studying
ring of
operators. And in fact, I'm going to use it right now. So I want to talk about this. I want to use these to define a deformed product of line operators. So remember, way back around here somewhere, I said that the line operators form a monoidal category, but it was a commutative tensor product. Well, I'm going to deform that tensor product by requiring that this generating function of spin characters satisfies this law. Okay, that defines for me a deformed product. And the essential physics here is this. If I have these two line operators, if they preserve the same zeta supersymmetry, the correlators are independent of x1 and x2. And so you could pull them far apart, and you would expect this kind of formula for the greater Hilbert space. But the surprise is that there's a one-dimensional space here which has a non-trivial character under the SO2. Remember the SO2, which is preserved by the presence of which is preserved in the presence of the two line operators. Okay, so that's what I call the basics of the line operators. Now I would like to talk about the three results mentioned in the introduction. First I'm going to talk about some formal mathematical construction, which goes under the name of strong positivity. And then I'll tell you about the Darboux coordinate expansion. That's the first formula I flashed on this slide. And then finally, I hope I'll have time to say something about the data theory. Okay, formal line operators. So now we get this purely mathematical construction where the data are the data that Andy said. So there's a local system, gamma over B. It has an integral antisymmetric product. It has a Z, which is a homomorphism from gamma to Z. And it has this collection of spin characters which satisfy this motivic unstable sorting or wall crossing formula. That's the data. Now with that data, I can divide up B times C star into chambers using these walls gamma hat. And by definition, a strongly positive formal line operator is a collection of these expressions defined on each chamber, which is a finite sum over gamma, and the coefficients of that are finite sums of Q integers. Okay? And that's what we mean by strongly positive. First condition. And secondly, they transform across chambers exactly according to the wall crossing formula I showed before in terms of the quantum dialogues. Now, this strong positivity is a non-trivial constraint. For example, the very simplest transformation law you have is a single hypermultiplet in the spectrum. And so then you're just conjugating by a single quantum dialogue. And if you work out what that is, there are two things that can happen. It depends on the sign of the inner product of gamma C with gamma H. So if gamma C with gamma H is negative, then you get a finite sum of spin characters of the antisymmetric wedge product of the antisymmetric product of row n, where n is the reducible representation. So this clearly preserves strong positivity. But if the sign is the opposite, you get an infinite sum of characters of the symmetric product, and these minus signs violate strong positivity. So that shows that if you're just trying to construct these things algebraically, you start in some chamber and you put some combination of these x's and you just try and generate the rest by wall crossing, in general, you will fail for exactly this reason. So let me show you that in more detail in the simplest example we can think of, which is a single U1 theory with a single hypermultiplet. And he also referred to that theory in his talk. That's the one that gives you the Oguri-Vafa-Sandberg-Schenker metric. So here we have B, which is C star. We have a local system of rank 2. We can take the generators to have inner product 1. And our BPS spectrum, omega of gamma, it's the same everywhere on this U-plane. And it's just 1 if gamma is plus or minus gamma 2 and 0 else, 157. So all we need to know then is the central charge function for gamma 2 of U, and that's just U. So I mean, if you can't get simpler than this, right? So we have U over zeta is negative. I find it a little more convenient to work on the universal cover. And on the universal cover, the walls are just straight lines where argument of U minus argument of zeta is an integer multiple of pi. So the purple lines here are the walls for plus gamma 2. The orange lines are for minus gamma 2. And here are your chambers. So now let's try and define a strongly positive line operator for a pair of integers PQ by just declaring that in this chamber, C0, it's X PQ. Okay? And then try and generate the rest by wall crossing. Will it succeed? Well, start with P equals 0. P is greater than 0. If P is greater than 0, then you work out the stability condition for halos. You find no halo, halo, no halo, halo, and so on. And so now if you cross this wall, you're adding a halo of gamma 2 particles. And the wall crossing formula nicely gives you this finite sum. And incidentally, these characters are nothing but Q binomial coefficients. So you get that expression. Now you could cross the next wall with the formula I showed you, and then each of these things transforms to an infinite sum of the characters of the symmetric representation. Then there's some terrible identities you might write down, and discover at the end of the day that you just got a single X. But the smart money says, no, you just have monodromy on this local system, so you must have had a single X over here, the monodromy image, and then you do the wall crossing back. Now the signs are such that you get a positive linear combination. Anyway, for P greater than 0, you get a nice formal line strongly positive formal line operator. Now to come back to your question about the chord and the halo. you see, crossing the wall this way, the core is PQ. And then I'm adding these gamma 2 particles. So you see here, PQ plus J. That plus J means I'm adding plus gamma 2 particles. Okay, so the core is PQ, the halo is gamma 2. Now, supposing I was going the other way around, from here to here. The core would be P comma P plus Q. The halo is minus gamma 2, and so I'm subtracting from that P. Okay? So as I traversed this zeta, as zeta traversed this chamber, what was core and what was halo has changed. That's why there's no invariant extension. Okay, you can work out the algebra of these formal line operators, and you know, when P and R here, if I'm writing FPQ times FRS, when P and R have the same sign, it's just the Heisenberg algebra. But when they have opposite signs, it turns out that it's a deformation of that Heisenberg algebra. I forgot to say something important. So I showed you that if I try and generate a formally positive, a strongly positive formal line operator by starting in this chamber with P greater than 0, it works. And I forgot to tell you that if I start here with P less than 0, it fails. That's the expression, that's the reason I expressed before. On the other hand, if I had started in chamber C1 with P less than 0, it would have worked. So at the end of the day, I get this spectrum of simple line operators. I can work out their algebra. And the thing I want you to remember for later in the talk is that if I multiply these two, I get a deformation of the Heisenberg algebra. And if I make a simple modification of the BPS spectrum so that omega of gamma is 1 when gamma is a multiple of gamma 2, which integer q bigger than 1, then I get a more serious deformation of the Heisenberg algebra. Okay, so there's this and similar examples lead us to conjecture that the algebra of formal line operators is canonically isomorphic to the algebra of true line operators. So everything I've been doing in this section here has been completely algebraic. Okay. Now, that concludes that section about formal line operators. I think I started halting at various points. Are there any questions? Have I lost everybody?
I lost, sorry.
Yes?
You lost me. You lost me.
Just admiration.
I can always count on you, Alex. Any questions about science?
Science.
All right, so that's really bad, actually, if we have questions. Is it completely obscure what I'm doing?
I was going to ask you,
Yeah.
about the different formula choice.
Yeah, oh, okay, I went through that very fast. So you understand what formal line operators are because they're very close to things that appeared in your paper. Now, on the other hand, we can think about the physical theory directly and try and work out these Wilson line operators. And we get the same set of objects. Okay. So by this purely formal construction, we seem to be
So you're saying this is
creating the whole set of physical line operators that we would have gotten from Wilson and Interpolars.
You're saying that this Feynman would introduce canonical basis as a space of functions in this small space.
Yeah, something like that. Okay. So now I want to tell you about this Darboux coordinate expansion. So now we work on R3 times S1. So now we have a loop operator. And so now these vacuum expectation values become functions on this moduli space that Andy was talking about. And so I want to claim that they're expanded in terms of these Darboux coordinates with coefficients which are the framed BPS indices. So the framed BPS indices are the protected spin characters at y equals minus 1. So what's the argument for that? Well, first of all, these things preserve supersymmetry. So they're functions on M, but because of the supersymmetry, moreover, they're holomorphic functions on M in complex structure zeta. Now, we can also say something about the R goes to infinity asymptotics. Remember, the circle has radius R, and similarly, the zeta goes to 0 infinity asymptotics. And the reason we can say something about that is that there's also an interpretation in 4 dimensions where we take a trace over the Hilbert space of, as usual, e to the minus 2 pi r h. Theta, that's the theta that Andy described. So it's in Hom gamma r to 2 pi z. And it's physically the boundary conditions on the electric and magnetic Wilson lines. And Q here is the charge operator, so it's equal to gamma in the charge sector gamma. And this quadratic refinement here enters because the theory is a self-dual theory. And so that's really the subject of an entirely different talk. But let me just say that in formulating abelian self-dual theories, when you write down the self-dual theory is always based on some generalized cohomology theory. That generalized cohomology theory has a natural inner product on it. And to write down the self-dual theory, you have to choose quadratic refinement of that inner product. And that's true of all self-dual theories. The self-dual theory in 6 dimensions with a Ramon field in 10 dimensions is a non-trivial subject. Here, you should always think of the infrared Seiberg-Witten theory as a self-dual theory. It requires a choice of quadratic refinement in order to define it. And in self-dual theories, where you sum over the topological sectors, you have to sum in signs or phases, and those are determined by these quadratic refinements.
In what sense is self-dual?
Well, one way to see, I think the nicest way to see it is those that come from 6 dimensions come from the 2-0 theory, which is self-dual. There's no natural Lagrangian. You have to make duality transformations to different frames, duality frames, as you move around in the U plane. The thing that's really there is gamma, not a splitting of gamma into its electric and magnetic parts. That's unnatural. And
maybe you mean that it's holomorphic. In that sense, it's self-dual. In Donaldson language, it's easier to say. It's tau and whatever other tau bar would be pure tau.
Well,
it's holomorphic.
I don't fully understand that, but I do insist that Seiberg-Witten theory should be thought of as the infrared Seiberg-Witten theory should be thought of as a self-dual theory. Anyway, we do want to put this quadratic refinement in here, and that's the source of this twisting that you are torturing Andy over. So now the point is, what are we trying to do here? We're trying to prove this formula, and what I want to do is I want to argue what the R goes to infinity asymptotics of this formula are. And you see what they do, of course, is, as usual, they project onto the ground states. And what are the ground states? The ground states are the framed BPS states. And now if you evaluate this operator on the framed BPS states, you get the semi-flat coordinates that Andy wrote down.
Can you remind what was H of L psi? Just a moment. H.
Right. So given a line operator, we have a Hilbert space H sub L. Line operators of type zeta preserve this algebra OSP4*/2 sub zeta. And so we get a Hilbert space H sub L sub zeta. Okay. And that's what we're taking the trace over. Now, if we evaluate this on those ground states, remember, the thing is, the energy of the framed BPS state is minus the real part of Z gamma over zeta, which is minus Z gamma over zeta plus Z gamma bar times zeta. So if you put that in there, you'll recognize the semi-flat Darboux coordinate expansion. So we know that we have this kind of expression at large R. And so we make an ansatz that L looks like this sum with some unknown functions, y tilde. We know they're holomorphic. We know their asymptotics as R goes to infinity, and zeta goes to 0 and infinity. And now we also know their wall crossing. Why is that? Well, I've said that these framed BPS indices have wall crossing. And I said that at y equals -1, that can be expressed by a simple diffeomorphism by these cluster transformations on these little x gammas, commutative little x gammas. But on the other hand, these vevs should have no wall crossing because there's no phase transition as you cross some walls of marginal stability in the four-dimensional theory. So how is that going to work? Well, it must be that the wall crossing of y tilde must cancel the wall crossing of the framed BPS indices so that this thing has no wall crossing. That means that the y tilde transformed with the opposite cluster transformation, which is true of the Darboux coordinates, as Andy showed you. And these three properties uniquely determine the y tildes to be y gammas. So that's the proof. Okay. So that is our justification for the idea that the y gammas can be thought of as infrared line operator vevs. And moreover, the non-commutative algebra of line operators that I talked about is some kind of deformation of the algebra functions on M. And so we already discussed this. So it's pretty clear that there should be a relation to the algebra from BB branes for the co-isotropic branes discussed by Kapustin and Nekrasov. So let me show this in our U1 example, the periodic tau nut example. So then we have the Darboux functions. Y01 is just the semi-flat one. Y10 is corrected by these instantons. And there are two functions, v plus and v minus, which satisfy this equation. So you could think of this as a complex equation defining the periodic tau nut space. And notice that it coincides rather nicely with the deformed Heisenberg algebra where we put y equals -1. And it looks even better when we put in q bigger than 1. So then the equation defining the classical manifold is this equation here. And indeed, if you take this algebra of formal line operators, put y equals -1, that degenerates to this. So that really shows that it is a deformation of the algebra of functions very explicitly in this case. Okay, I'm out of time, so I can't tell you about the A1 theories. But I guess I have to justify my presence here. So let me just say one thing if I can. I have to say something about Liouville. Yeah, so we have ways of calculating, these framed BPS degeneracies in cases which are related to infinite systems of the gauge group is rank 1. Okay, and now they turn out to be three-term expressions like this. And let me just say that the same kind of three-term expressions we found in Jörg Teschner's paper, which for the quantum geodesic length operators in the quantization of Tycho theory. And so we think
No 5-term
related. So that's all I have time to say.
5-term, no 5-term relation.
No, it's not like the pentagon. It's just three terms in the expression for the vacuum expectation value, which match precisely to the expression in terms of Fock coordinates for the quantum geodesic length. Okay, so if you want the quantum geodesic length of some red curve like this, and you've chosen the triangulation to define the Fock coordinates, that looks a little like this with these blue curves, then you get an expression that looks like this, and we also get that. Okay. That's the relation to quantum pipeline theory. So what did I say? So I defined these line operators L zeta and their protected spin characters. They satisfy this Seuberman wall crossing formula. These f of L's define a deformation of the algebra functions on M. There's this mathematical construction of strongly positive formal line operators, which we think is the same. It is a way to construct the physical line operators of the n equals 2 theories. And I didn't describe this 3, but I would have said that we have algorithms for computing these frame QPS degeneracies and protected spin characters in that class of theories. So lots and lots of open problems here. I'd like to clarify the relationship to Tyclone theory, to quantization of Tyclone theory and Hitch and moduli spaces. I'm sure I can learn about that from people here. I'd also like to clarify the relation to canonical bases and total positivity. That's clearly related to R positivity. It's I don't know the math. It's clearly related to things that Dr. Goncharov has conjectured or proven. I'm not even sure what to say exactly here, but there's relations to those works. Now I said that we know how to calculate for A1 theories. But the higher rank case is really important and qualitatively different. And so this is not just a matter of dotting I's, crossing T's. That there's probably some serious issues that come in at higher rank. And so we have some ideas for how to proceed there, but this is, I think, an important problem. This quantum dialog also appears in the expressions for Wilson loops and non-compact Chern-Simons with the theory. And it's natural to wonder if there are relations there. The extension of this work to supergravity is important. We don't have a physical, I'm not aware of a good physical explanation of why the KS wall crossing formula should be true in supergravity. And I think that's an interesting problem. Some of these conjectures on strong positivity and so on have implications for non-pole moduli spaces, and that would be a way to check with precise, rigorous mathematics some of what we're saying here based on physical pictures. And finally, David is going to, I think David is going to talk about surface operators and 2D, 4D wall crossing. Yeah, is that long? Okay. David is going to talk about something else. But I think there are things to do.
What's the last question?
Greg, you mentioned for Goncharov coordinates. What did they play a role in this story?
Yeah, so you can construct, okay, so I guess Andy didn't explain that. So the short answer is that theories that come from 6 dimensions, for theories that come from 6 dimensions, you can construct these Y's and gammas very explicitly, and they are Pock-Goncharov coordinates. Now,
For A1.
thank you. For TGN and A1 higher rank. I'd be happy to tell you more, but there's actually it's a bit of a story.
So the rate of dependence is just pure scale. It's scale down. There is a radius.
Okay, so the R dependence. Yeah, the R. Okay. So what we do here is we put 2 zero theories on C with punctures. Okay, and so the Hitchin system has R squared in it. And we also have phi, we have regular singular points, like that. We can also do irregular singular points. Now, you could scale R out of phi, out of these equations, but then it goes into here.
So these are
Yeah. So, right, so that's where the R dependence comes in. So as Andy described, you have a 2-to-1.
So I was just saying that I don't remember seeing conventional in Untitled.
Yeah, I'm coming to that. So you could also ask where in Pac-Contra is there zeta dependence or... No, they don't have zeta.
Yeah, must be. I don't have that question.
Oh, you don't have Well, does anybody else have that question? Should I explain that? Why not?
We have discussion section in the afternoon.
Okay. Somebody can ask me.
I was hungry. You're hungry.